Hey guys, so I've been receiving a lot of emails about plans for the open source Redox Flow battery. Um, so I thought I'll make this video to show you guys some of the new designs so you can attempt to build your own versions of this. Um, so the battery we are designing here is zinc bromide battery. Um, so if you go to Wikipedia, um, it will tell you that the zinc bromide battery is about 60 to 80 watt hours, uses a carbon cathode and a zinc anode, and it uses zinc bromide as its electrolyte. Well, of course, there might be many variants of how this can be built, but this is one of the many ways. So the simplest version of zinc bromide battery consists of a container with a carbon cathode and a zinc anode swimming in zinc bromide. So during charge, the zinc electroplates onto the zinc anode, and the bromine produced is produced as a result, and that bromine settles down. So if we want to reverse the reaction, we connect some kind of a load here, and the bromine that's in contact with the carbon cathode will start reversing the reaction. So we'll get back our zinc bromide. So one of the many advantages of this battery is it has literally unlimited life, because we are essentially just electroplating and stripping zinc. But the only downside of this is that it periodically needs to be discharged so that it does not produce zinc dendrites. So these dendrites, once they start growing, they always grow towards the cathode and eventually short circuit with it. So that is the reason they need to be discharged every once in a while, and that's one of the disadvantages. So one of the other disadvantages is that the discharge of the battery is directly proportional to the surface area of the cathode. So only the surface that is in contact with the electrolyte reacts. So this is the first version that I built. You can clearly see the zinc anode here and the graphite cathode here. So this was a very basic bad version, but it definitely worked. So I'm not sure if you guys can see this, but there's a motor here that's running, and you can see the bromine suspended in the solution. So as long as it is suspended in the solution and in contact with the electrodes, we can reverse the reaction. So following that,
Okay.
I actually built this other version. Um, so initially, my ideology was to create a really small space in which I can, place the electrolyte, the electrodes, and do a discharge test. And
So
initially,
if you guys have any
I
suggestions,
built the cell with two plastic plates, and there's a rubber gasket in between, and on the top there's a zinc anode and a piece of graphite at the bottom that acts as the cathode with some carbon coated on it. So this worked pretty well too, but it was a question of scalability. So was this idea scalable? And the answer actually came when I built the bigger version. So I hooked a bunch of these batteries that I built, and so I'm powering a router. Uh, so this battery puts out about 1.8 into 4, about 7.2 volts. And it worked pretty well. The router ran for about 30 minutes. So that was really, really promising. But again, one of the main problems with this design was using too much of materials, too much of weight that didn't contribute to the energy density. So this build, overall, it reduced the um, 80 watt hour per kilogram. It's no longer the 80 watt hour kilogram battery because of all this weight. So I had to come up with another solution. And in these builds, I was actually using plain graphite plates coated with carbon. Let me see if I have a video. Oh, yeah. So I use graphite plates like this with carbon coated on them with some kind of a waterproof binder, and that becomes the cathode, and a piece of zinc for the anode. So in my latest design, though, I've revised a lot of things to make it more scalable. So now that we know some basics about how the zinc bromide battery works, and how I have built some basic prototypes, we can now look at the new version I have. So how do we turn this into a flow battery is the question, right? Um, so one of the specialities of the zinc bromide battery is that after you charge the battery, uh, the electrolyte is full of bromine, right? So we can separate this bromine out, and we can refrigerate it in another tank. Uh, so until we need the energy again. So if you need the energy back, you pump the zinc, the bromine electrolyte back into the um, electrode casing, so this will become more clear when I show you. um, representation. So another improvement from the previous version is that I told you I used graphite, but so I was also talking about some disadvantages, and I was telling you about one of the disadvantages being the surface area limits the amount of current. That's true for any battery, but especially with the zinc bromide battery, it has a very low power density, um, which means the amount of power it can put out at any given instance is limited. I don't exactly know the number on the top of my head, but it's low. So it's one of the reasons why um, to power something like an electric car, for example, you would need a lot of surface area. So that brings us to the graphite plates again. So the graphite plates are coated with carbon, and the thickness of the layer is about zero point 0.1 microns, I think, or 10 microns. Um, so the amount of current that your battery will produce is directly proportional to the surface area of the graphite you use. To overcome this, we can actually use a three-dimensional electrode. Um, so in one of my latest videos, I've shown you this material. So it's a graphite felt, and it's about 2 millimeters thick, or about 20 times thicker than the carbon coating on the graphite. So for the same surface area of the graphite we used, we should get 20 times more current density, like more power. So, so how do we turn this into a flow battery? So these are the designs finally for you guys. And here are some rough measurements, but feel free to play around with them. So the assembly consists of an enclosure, and the enclosure has an inlet on the top and an outlet at the bottom, and there's a cassette assembly that holds the electrodes together, and you insert it into the uh, cassette enclosure, and this is how it looks after it is assembled. Here you can see the graphite electrode, and on the back you can see the zinc electrode. So for the graphite electrode, my graphite electrode is 2 millimeters thick. So I have a piece of plastic like that, and there's a 2 millimeter groove, and there's also a groove at the tab end, so that I can pull a terminal out. So I'll use some graphite inside this as my current collector in the shape of the tab, and a rectangular piece of carbon foam on that, and over that I'll put my separator, and similarly we have another plate in which the zinc anode will sit. So this is only 0.3 mm because we don't need very thick zinc plates, and you sandwich these plates together and insert the assembly into the enclosure. So for the outlet, we will use some kind of a regulated valve to regulate the outflow rate. And similarly, we will have another regulator to regulate at what flow rate the electrolyte is coming in. We want to try to make sure we adjust the regulators in such a way that this does not overflow, and it is also in line with how long it takes for each molecule of zinc bromide to dissociate into bromine and zinc. So these are the factors you have to keep in mind. So I'm gonna go ahead and design these in 3D, and once that is ready, hopefully I'll make another video update. Thank you guys. Okay, so one last thing that I forgot to tell you is the charge and discharge cycle. So during the charge cycle, you can do this in batches or you can do this continuously. I haven't tried it out, but if you have to do it continuously, a continuous flow battery, then I guess the flow rate has to be like really, really slow and it has to be really fine tuned. Another way to do this is by using batch processing. So you dispense a known amount of zinc bromide into the electrolyte tank. So you know technically how long it will take to charge. So let's say it takes 30 minutes. So after 30 minutes, we open the outlet and let all the electrolyte flow into the refrigeration tank, into a bromine tank, and then close the bottom valve, open the top valve again and dispense another another batch of electrolyte, push it into your refrigeration tank, and finally when you want to discharge it, pump the bromine electrolyte through the inlet back into the battery. And of course your outlet also will have to be batch processed. So once you discharge your first batch, you can actually drain this into a separate tank called spent electrolyte and continue doing more batches.